So thanks a lot for the invitation, and also thanks a lot to Saga for the very nice also introduction, which I think will complement quite well what I will discuss now. And as you can see, I'm going to focus on on CTA, of course, so the Cherenkov Telescope Array, which is a complementary instrument to the MAIS telescope, the same kind of technology. But in this talk, I will focus more on one particular science case in which we will enter more into the detail, which is the quest for the diffuse gamma ray emission from galaxy clusters. So as you know, the universe is highly structured with a network of void, filaments, and nodes. And if you look at the nodes in this matter density field, you can find galaxy clusters, what we call galaxy clusters, which are made not only of galaxies, but also of dark matter and of the intra-cluster medium, which is what will be the core of this talk. So these clusters, they are quite massive, typically 10 to the 14, 10 to the 15 solar masses, with large sizes of megaparsec typically. And they are made of this tenuous intra-cluster medium, quite hot, a few keV in temperature, and magnetized. And in fact, when you form this galaxy cluster, not only you will convert the kinetic energy from this structure formation into heat, but you will also produce shocks, turbulence, gas motion, and so on, magnetic field and cosmic ray in this energetic events. And so the question that we want to address here is how do particles get accelerated and transported in this intra-cluster medium? And also what are these contributions to the energy budget of galaxy clusters? And in fact, the radio emission is already showing this non-thermal phenomenon in galaxy clusters, showing the presence of cosmic ray electron and magnetic field via the diffuse synchrotron emission that you can see, for example, in the coma cluster on the right image. And this is useful to understand particle acceleration, but there is a lot of questions also that are rising given this observation. So, for example, cosmic ray electrons are short-lived, which requires therefore in situ production when you see this kind of images on the right. And if you accelerate cosmic ray electron, you should also accelerate cosmic ray protons somehow. And these cosmic ray protons should interact with the thermal gas to produce secondary particles like pions, which will eventually decay into electrons, but also neutrino and gamma rays. And so there are many different processes that can enter into the game, like turbulence, injection from AGN, shocks, and also these hadronic processes. So this interaction between cosmic rays and the thermal gas are expected to produce gamma rays. In principle, you can learn a lot from this about plasma physics and also the dynamics of the ICM, which is useful not only in itself, but also even for cosmology. I will not enter too much into this topic. But anyway, my main point in this slide here is that, in fact, the detection of these gamma rays will allow us to study cosmic ray protons and provide an unambiguous diagnosis on cosmic ray protons, which will be key in understanding this particle acceleration mechanism, complementing quite well what you can see in the radio, which is tracing mostly cosmic ray electrons and magnetic fields. So you expect, in fact, some, from numerical simulation, people have been trying to address this question and to make prediction for what we expect. And usually you can model, this is what I will follow in this talk, cosmic ray distribution, cosmic ray proton distribution as a function of energy and distribution in the cluster. This kind of parameterization, so typically power law or in energy or momentum space with some slope, this alpha parameter, and you can connect the cosmic ray distribution to that of the thermal gas with parameters like, for example, this eta parameter here that you can see. And usually what we do is to estimate or address the amount of cosmic rays that you have in cluster relative to the thermal gas. So this is basically the fraction of energy that goes into cosmic ray when you form these clusters. So you have here the typical numbers that you expect and a simulation here that was made that illustrates what kind of signal you expect. The problem with this is that large unknowns are at play. For example, the efficiency of shock acceleration. You can see different model as a function of the Mach number here, showing that you have a lot of quantities coming from this. This is the same also for the cosmic ray distribution in cluster, where you can see here the profile as a function of radius for different models, and in this case you see also the large dispersion that you have and which is not well known. Okay, oops, sorry. In fact, so not only simulations were made, but many attempts to detect the signal were done also, either in individual targets, using stacking, cross-correlation, and so on. You see an example with Fermi lat in the plot on the bottom right, where you see that at this stage today we reach typically limits of a few percent for this normalization parameter, this X parameter. So basically, cosmic rays are expected to be less than a few percent relative to the thermal gas in galaxy clusters. And in fact, so far it was only mostly a non-detection, but in fact there is one case which is maybe quite interesting, which is the case of the COMA cluster, in which in this case there is a gamma ray signal at the location of the COMA cluster. You can see the Fermi contours on top of the COMA cluster as shown by the Planck satellite. But so this data favor this turbulent ray acceleration model, but the problem is that with Fermi, the resolution is not good enough so that you cannot really make sure that the signal that you observe is coming from the intra-cluster medium and not from, for example, AGN contamination. All right, so and this is basically the follow-up of this that I will address now in the context of CTA. So in fact, as we have heard also in the previous talk, there are different ways to observe this gamma ray emission. Either, for example, from space using, for example, the Fermi lat telescope. You can see on the left, which is a pair conversion, which uses pair conversion detectors, operating since about 40 years. At relatively low energy, you see between 100 MeV and 100 GeV, roughly speaking, with resolution of about 1 degree, typically at 1 GeV. On the other side, at higher energy, you can use imaging atmospheric Cherenkov telescope. I will not enter too much into the detail because it was already discussed a lot in the previous talk, and in which case you will use pointed observation at higher energy complementing Fermi, and you expect to reach better angular resolution if used in particular stereoscopy, like we will do for CTA, as I will show. And so with these two complementary techniques, basically you are sensitive at energy between, let's say, 0.1 to 10 to the 5 GeV. So let's come to CTA. I will not discuss too much about CTA in terms of instrument, but this is in CTA in a nutshell. So CTA is the next generation imaging atmospheric Cherenkov telescope instrument, which is being built at the moment. So we have two sites. One of them is in the Paranal Desert in Chile, and the other one is in La Palma in the Canary Island, as you can see on these two artist images. So the array is more than 50 telescopes in total. We have different telescope sizes in order to sample as well as possible the sensitivity in terms of energy. And we are sensitive in the end from 20 GeV to 300 GeV with a field of view, roughly speaking, of well, typically a few degrees for up to 10 degrees, typically. So the consortium is quite large. We have 32 countries involved with more than 1,000 members in the consortium. One telescope is already taking data at La Palma, in fact. And this will be a proposal-driven observatory with a large program. So one of these large programs will be Galaxy Cluster. I will talk a bit more about that just right after. Okay, so CTA was talking about Galaxy Cluster, but it's not only about Galaxy Cluster. We have many key science projects that may be of interest for you. For example, focusing on the Galactic Center, Galactic Plane Survey, also some program related to the physics of dark matter searches in the gamma ray, some extragalactic survey, mainly focusing on the physics of AGN in themselves, also star forming system, Pevatron, transient also, and also a survey about the LMC. So all these CTA key science projects are related to the origin and the role of relativistic cosmic particle, extreme environment, and also frontiers in physics. And as you can see, one of them is focusing on galaxy clusters, and I will enter a bit more into the details regarding this one. Okay, so as I was saying before, so far there is no clear detection of gamma ray emission from galaxy cluster, at least no unambiguous one. And with CTA, this is really the goal, to take advantage of the characteristics of CTA to produce the first non-ambiguous cluster scale gamma ray detection. So this is basically the search for the diffuse gamma ray emission associated with the interaction between cosmic ray protons and the thermal gas in the intracluster medium. There is also, a science case with this related to the constraint on dark matter, because as I was saying before, galaxy clusters are also mainly made of dark matter, and therefore they are useful targets to address these questions. But I will talk mostly about the quest for this cosmic rays in cluster. So in the case of CTA, we focus on the Perseus cluster because this is the most promising target. This is, well, we can argue about this based on a scaling argument with respect to other wavelengths. Also, this Perseus cluster presents a really dense core, which is interesting for us because therefore we maximize the hadronic interaction in this dense core. In terms of extension on the sky, localization, this target is great. Also, we can observe it from the CTA northern area in very good conditions, and also it disposes of many ancillary data. For example, you can see on the right image the Perseus clusters as seen in the X-ray band here, and also the fact that this cluster presents a radio mini halo that you can see with the green contours. That is already showing that we have a particle acceleration ongoing in this cluster. And so in total, we have 300 hours planned for the observation of the Perseus cluster with CTA that have been proposed in the consortium. So in terms of sensitivity, this is what we expect. So this is a differential flux as a function of photon energy, and you can see the different sensitivity curve that we have from Fermi lat, for example, in 10 years observation of the extragalactic sky in red. Current facilities such as S for 100 hours observation, and what we expect for CTA in 100 hours and 1000 hours here. On top of that, you can see the different models that we have produced for the typical Perseus cluster with different parameters that are describing the cosmic ray underlying distribution that is unknown. And so you can see that with Fermi lat, we expect to be for this kind of cluster at the limit of detection. And with CTA, depending on the model, we are really getting into the regime where we can expect to have a nice detection. And so this is due also, interestingly, mainly to the great angular resolution that we have, which allows us also to disentangle contamination from other sources, and large field of view and energy range to do this. So with these properties, this is really key to detect the diffuse emission and disentangle these different sources that we can have. So let's enter a bit more into what we do in practice to address this question. So first of all, we need to model. So I just before on the slide before, I was showing this kind of modeling, but in order to produce this is what we do. You need to account for the injection of cosmic ray protons in particular, and also you can account for cosmic ray electrons. Account for the interaction between the thermal gas and the cosmic ray protons, which will eventually produce this gamma ray emission via this pi-0 decay that you can detect either with Fermi or with telescope like CTA. And also, when you produce this interaction, you will also generate a neutrino and secondary electrons. The electron is missing, but there should be an electron here that will interact with magnetic field to produce radio synchrotrons that you can see, for example, with radio facilities, and also inverse Compton with interaction with the CMB. You can have also cosmic ray electrons related to other origin that will also, follow the same process in the end. So in practice, so this was an illustrative view, but in practice, this is what we do. So we need to model with input quantity these different inputs: cosmic ray electron, magnetic field, cosmic ray protons, thermal gas, either pressure for the normalization, because this is connected to the thermal energy, which is a useful quantity, and the thermal gas density in order to account for this hadronic interaction, and then follow the different ICM processes that will eventually lead to the observables that are useful for us. So in the radio, millimeter, X-ray, gamma ray, and neutrino. So for this, we use the public software called MINO, which was published in this paper, and it's publicly available, so you can have a look if you are interested. So with this, we have a self-consistent multi-wavelength framework that we can use to calibrate the model for CTA. So first of all, we need to calibrate the thermal and magnetic field model, which enters into this production of gamma rays. For this, we can use literature data. So for the thermal models, it's quite simple. We can use X-ray data. You can see different models of the electron density as a function of radius, gas temperature also here as a function of radius, the thermal pressure as a function of radius. So for the thermal part of the model, thanks to X-ray and Sunyaev-Zaldovich effect data, this is quite well known. We can have a very good description of the model. We can also validate this with Planck data. You can see here, which is basically showing the pressure of the cluster. And you can see that on this profile here, given this model based on X-ray data, we are able to have a good description of the cluster. Then for the magnetic field, this is another issue. As you may know, this is much more difficult to obtain. And for this, we need to make different assumptions and also use data available in the literature to account for this magnetic field. So you can see the different magnetic field profile that we consider in this work, that are based on different assumptions. Okay, so once we have this thermal and magnetic field model, we need also to model the cosmic ray proton, which is really the core of what we want to detect in the end. And once we have modeled this cosmic ray proton, we can then produce what we expect for CTA. So the point is how to calibrate these cosmic ray protons. So either we can assume that we are in the pure hadronic model, which means that all the radio emissions that we see in the Perseus cluster is due to these secondary electrons that are coming from this interaction between cosmic ray proton and the intracluster medium. Or either we can have estimates on these cosmic ray protons according to what we expect from numerical simulation. So we follow the two different strategies. And for this, so for example, in this case on the left, you see what we do in the case we use the pure hadronic model together with radio data. So you can see the cosmic ray proton distribution, once everything else is fixed, will produce this hadronic interaction, therefore via then some losses produces secondary cosmic ray electrons, which will end up producing synchrotron emission, and therefore the radio signal that we have. So if you use radio data to constrain this signal, you can therefore go back in the end to constrain the cosmic ray proton distribution. And if you constrain this cosmic ray proton distribution, you can then follow the other track on the right to compute what you expect in the gamma ray. This is exactly what we do, and you can see the differential spectrum on the right that you will expect in this case. So you can see in blue the constraint that you obtain for this pi zero decay, so interaction between thermal gas and cosmic ray protons, and this is what you get for CTA in blue. In pink here, you see this is the counterpart from the inverse Compton emission that you have also here. But in practice, inverse Compton is always subdominant with respect to what we expect for this hadronic processes with CTA. Okay, and on the other side, you can see also what we expect in this case according to this prediction from numerical simulation. So typically, this kind of fluxes in green, either hadronic or inverse Compton contribution. So once we have this, we can therefore make prediction for CTA and simulate what we expect in terms of events. But before, just to give you an idea, so this is the fit of the radio data that we can do. So we can fit simultaneously the spectrum and the profile to produce these gamma ray predictions that I was just showing before. So this is just the same as I was showing before, but showing also the fit to the radio. One word about the magnetic field. As I was saying before, the magnetic field, the knowledge of the magnetic field is important when you use this hadronic, pure hadronic model. And this is, in fact, producing most of the systematic uncertainties that we have in the end on this prediction. You can see the different curve here for different magnetic field assumptions. And basically, so statistical uncertainties are already large in this prediction, but you can see that the magnetic field even add a factor of 2, roughly speaking, uncertainties in this prediction. So it's quite important to account for this when we do these predictions. And same thing for the profile here that you can see.
You've got 2 minutes.
Okay, good. All right, I'm nearly reaching the end. Once we have this model, we can apply this to CTA and make this simulation. So this is what we do with this code that's called Kesako, which interfaces the sky model and the observation setup to run the simulation and also allows you to perform analysis. In the case of the Perseus cluster, this is the kind of data that we have. You can see that the Perseus cluster is sitting here, but you have also 2 AGNs that are contaminating the data, which we account for. And all around here, this is related to instrumental background. In terms of counts, you can see that as of energy, you can see that we are dominated by this background, and we need, of course, to disentangle everything in the analysis. So the cluster is the contribution in blue here. Once you subtract the background, just to give you an idea, this is the kind of data that we expect. So this is for the pure hadronic scenario. You can see we expect in this case a detection of a bit more than 10 sigma detection, which you can see how it will compare to X-ray observation and Sunyaev-Zeldovich observation. So in this case of pure hadronic emission, we expect a relatively compact signal associated really to interactions in the core. So once we have this prediction, we can also produce this exclusion plot. Imagine that we don't detect anything. This means that we will be able to exclude the different parameters that we have in the model. So this is what is shown here. So the limit on this normalization parameter is a function of the slope of the cosmic spectrum and different shapes for the cosmic ray proton distribution. Okay, and since I'm a bit late, I will not enter too much into the details, but basically just to say that with CTA, we expect to be able to exclude the pure hadronic model in case it's not what happens in this cluster. And roughly speaking, we improve by 1 order of magnitude with respect to what is the state-of-the-art limit. But then we expect to detect something, hopefully, and in this case, thanks to the constraint on the spectrum and the profile, we will be able to constrain the underlying physics. So stronger shocks and more efficient acceleration will move you in this direction, and more diffusion of the cosmic ray will move you in this direction. So you expect to have a major step forward in the cluster cosmic ray physics with CTA expected. Just before finishing, we can also go beyond this key science project in the Perseus cluster, because we will have a survey of the extragalactic sky with CTA, and in this survey you expect to have clusters also. And we have already tested that making early tests that thanks to this kind of data, we will be able to also to improve a lot on what is expected, basically constraints that are typically in competition with this Perseus Key Science project. Another interesting topic will be also to explore the interaction between AGN and the intra-cluster medium. So you see these giant cavities in the core of clusters that are produced by this interaction with AGN. This is also something that we can address with CTA. And again, early tests show that possible detection of these cavities could be done in a few tens of hours, depending on the model. All right, this brings me to the summary. So I've been discussing mostly about gamma ray emissions from galaxy clusters, showing that the presence of cosmic ray protons imply gamma ray emission. And therefore, with gamma ray observation, you can have unique access to cosmic ray proton physics, acceleration and transport. So far, these cosmic ray protons are elusive, but maybe there is a hint of detection in the direction of the coma cluster. CTA is now under construction, and we expect unprecedented performances at TeV, in the TeV range. The first telescope is already taking data, and various science cases are being explored, including galaxy cluster 1 and galaxy clusters. This is the Perseus Key Science project, for which simulation and analysis have been developed and shows that we should expect 1 order of magnitude improvement with respect to the state-of-the-art limits, which hopefully will give a unique probe for the cosmic ray proton physics in galaxy cluster. And I will stop here. Thank you so much.
Thank you very much. It was an excellent talk. Yes, we have just time for one quick question. So it's going to be Sagar.
Hello, Remi. Actually, I wanted to know that you have using different size telescope and different field of view. So, what kind of background subtraction method you are planning to use for this galaxy cluster analysis?
Okay, I'm not sure to understand very well the question because the sound from the auditorium is not so good. So, your question is related to what kind of background we have in the data. Is that what I understood?
Yes, yes. What kind of background subtraction, that background modeling you can use it for since there are multiple different size of telescope with different field of view. So what kind of background modeling you are going to use actually for the signal extraction?
Okay, so in this work for the Perseus cluster, what we are doing, we are not. We are directly considering the instrument response function as we expect from CTA. So we are not working with simulation of atmospheric simulations. We are directly working with the expected instrument response function. So, for example, the discrimination between cosmic rays and gamma rays at this level are not addressed in this. But then what we address, of course, is a contribution from the background on the sky background. So in this instrumental background, basically, this is based on the instrument response function. So this is already included, if you want, this discrimination between hadrons and gamma rays. And this is really what we account for. Then on top of that, you have also the background coming from the sky, in which case we know that there are 2 different AGNs at least observed that are contaminating the data, NGC 1275, which is a BCG of the cluster, and IC 210, which is another galaxy from the cluster. And on top of that, also, we have considered the diffuse emission from the galaxy, for instance, which should be negligible in the case. So yeah, basically, this is a different kind of background that we have accounted for.
Thank you.
Long live India and France friendship.